Okay, let's begin. Gaurav, you can hear me.
Yes.
Screen is shared.
Yes.
Okay, so thank you for being here, Gaurav. This is essentially for the CAS squad. Uh, they have problems understanding resonance structures. So, CAS people, listen up. Okay, and that goes for all of you. I'm gonna say the names particularly, and all of you who are there, you need to see this video. You need to be very clear with all the resonating structures that I'm gonna do in this session today. Dikshita, Riya, Sanvi, Monishka, Agastya, Harsh, Vishnu, Arya, Parth, Charles, Naren, and who else is left? Sarvesh, Hamza, Hana, and Manya. All of you, if anybody else is left, I don't really think so. But okay, every one of you, listen. And in this segment, in this particular video, I'm going to give you a question that will be there in the middle of the video. Look at the question, keep an answer ready in the next class. That means Monday. Okay, Monday would be 2nd of June, 2025. Now, let's roll, Gaurav. You're ready? So,
Ready.
yes, we are looking at nucleophilic substitution reactions, the one that we already did in CAS class. So the point being, haloarenes, aromatic halides, they are much less reactive towards nucleophilic substitution reaction. We have already established that quite a bit. Okay, why the reasons they are already aware of? I'll tell you regardless. There are four reasons here. The screen is shared properly, right? I hope so. You're able to follow what I'm saying, Gaurav?
Yes.
Okay. The first reason is a partial double bond that exists between the halogen atom and your benzene. So this is partial double bond is the reason number one why they show less reactivity. Second is sp2 alpha carbon. And we've covered this in class today itself, but regardless of that, the third reason is instability of, you'll find all of these points in the NCERT textbook itself. Instability of phenyl carbocation. And the last one that we have is, uh, yes, electronic repulsions between the new nucleophile that is supposed to replace in nucleophilic substitution with the benzene ring. These are the 4 points why these 4 points are important. They could give you a 2 mark in your board exam. Why they are important? This answers the question why haloarenes are slow to react towards nucleophilic substitution reactions in comparison to haloalkanes. So this is not a standalone thing. In comparison to haloalkanes, they're slow for NSR. Now, still, it happens under drastic conditions. We've already looked at what exactly drastic conditions mean. Drastic conditions just mean this would happen at 623 Kelvin, a very high temperature, and at 300 atmosphere pressure, a very high pressure, because normal atmospheric pressure is 1 atmosphere pressure, considered to be 1 atmospheric pressure. So still, under these drastic conditions, still nucleophilic substitution reaction happens. For example, if you look at this reactant chlorobenzene with aqueous NaOH or with NaOH, it undergoes in 2 steps this nucleophilic reaction happens. First, it converts into something called sodium phenoxide, where just the ONA group is attached. Usually what we do is we combine this 2 step reaction into 1 step. We take one arrow and then we divide it into 2 parts, part 1 and part 2. Part 1 is where we use sodium hydroxide and 300 atmosphere pressure and 623 Kelvin. Part 2 is once the part 1 is over, meaning once you have attained your sodium phenoxide, then comes the second part of dilute HCl, or you'll find this also written as, instead of dilute HCl, they'll write it H plus in H2O. That means exactly the same thing. A little bit of acid in water is taken in the second step, where you see this second reaction happening, where what happens? The sodium phenoxide that you obtained in the first step gets converted into phenol, which is where we have conducted our nucleophilic substitution reaction, the new nucleophile OH minus. This is your new nucleophile, which has replaced Cl minus or the chlorine nucleophile, which was already there in chlorobenzene. Gaurav, you got this? This explanation was clear to you?
Yes.
Okay. Now I move to the next point. This is called Dow's process. We've covered this. The next point is that if there are electron withdrawing groups at specific positions like ortho and para position, if you have electron withdrawing groups at ortho and para, it is going to increase nucleophilic substitution reaction for your haloarenes. Examples of electron withdrawing groups, the one that we are looking at for 12th CDSE is nitro group, but electron withdrawing groups like cyanide, COOH can also give you higher rate of reactivity of haloarenes towards nucleophilic substitution reaction. By higher rate, we mean this. They happen at milder conditions, meaning we don't need to take 623 and 300 pressure. We now can do the same reaction with less drastic conditions. For example, the first reaction, we have seen all of this, but I'm repeating it regardless. First reaction is of para-chloro-nitrobenzene. So one NO2 group is there, one of the electron withdrawing group is there at this position is called para position. It is there at para position. How does it affect? Now, okay, sorry, 1 second. I'll just silent my phone. I'm not canceling the video as of yet. Will still progress with the thing. Okay, so what happens here is you have NO2 and the Cl gets replaced with OH. So you have nucleophilic substitution reaction, but it now happens at a lesser temperature. Now, the second point, we've already done this. The second point is more the number of electron withdrawing groups. As in when electron withdrawing groups increase in number, the conditions become even more milder. You do not have to go to such extreme conditions anymore. For example, let's have a look at the second reaction, where the second reactant, now you have two electron withdrawing groups. Gaurav, can you tell me what are the positions where these two electron withdrawing groups are?
Ortho and meta.
Yes, this position is ortho position. Some
Sorry,
people
ortho
had,
and para.
okay, I didn't catch that. This position is ortho position and the bottom position is para position. Some people had doubts in positions of ortho and para. This is with respect to chlorine. With respect to chlorine, this position is called ortho. With respect to chlorine, this position is called para. Okay, now when we have two electron withdrawing groups, one at ortho, one at para, it makes the reaction go even faster, meaning it will need less of high temperature. So the temperature dropped from 433, now it dropped to 368 Kelvin. The product is going to look the same. Here we'll have NO2 at this position, nitro at this position, but instead of chlorine, we have OH group over here, right? You've got this, Gaurav? I'll
Yes.
just move to the next thing. I hope they are also following along. Now, when we look at the third reaction, we have one more nitro group at ortho position. So you have two nitro groups at ortho, this ortho and the other ortho. So this is ortho position. This is also ortho position. Two nitro at ortho, one nitro at para. So three electron withdrawing groups at two ortho and one para position. This makes it so easy for the reaction to happen that you do not need any elevated temperatures. You just have to warm it with, can you see, water. Now you do not need NaOH also. You just need water and just a little bit of warming. This becomes very much eager to undergo nucleophilic substitution reaction. So just like how we've done in the previous cases, NO2 at two positions, and the para position, and then Cl is replaced with OH, NSR, done. Got this, Gaurav?
Yes.
Okay, but the story that we've talked about is only uh, taking place at ortho and para. So essentially, when you have electron withdrawing groups at meta, you see almost no effect on the reactivity of haloarenes towards nucleophilic substitution reaction. There is a question, and a very important question. It is often asked in the exam. Why do you not see any effect of electron withdrawing groups at meta positions? Why only at ortho and para? And to answer that, you need to get into resonating structures of electron withdrawing groups, specifically of nitro group at ortho, one set. One nitro at ortho, one set. One nitro at para, one set of resonating structures. And one nitro at meta position, one set of resonating structures. We are going to do just that today. Okay, 1 second. Let's continue. Shall we roll, Gaurav?
Okay.
Okay, so let's look at how the mechanism will look like for electron withdrawing group at ortho position, electron withdrawing group, we are taking nitro group. So if I start with your our uh, chlorobenzene here, we have chlorine, and chlorobenzene or any halobenzene will have three pairs of uh, electrons or three lone pairs of electrons, right? Gaurav.
Yes. Three
And
lone
the new
pairs.
nucleophile, yes, the new nucleophile that is going to substitute chloro and take its place so that NSR forms is OH minus. When these two are together, there is a step that takes place. What happens is this OH minus now attacks the carbon where the chlorine itself is attached so that one gets substituted by another and you have nucleophilic substitution. That is clear, Gaurav?
Mm-hmm.
If that happens, this happens uh, very slow. This takes place slowly. This is not a fast step. This is a slow step, a relatively slower step. When that happens, what you will see is that you have benzene and OH gets attached on the same carbon as the chlorine. The chlorine is still there, but now the OH is also attached to that particular carbon. So in that case, this bond which is there, right? This bond which is there, if the bond still remains at that position, the carbon becomes pentavalent, which is not really possible or energetically stable. So what happens there? How can we start resonating structures? What you see there, 1 second, I can't access my pen. Wait. Okay, never mind. This double bond breaks and goes to the adjoining carbon atom, becoming a negative charge. This I've talked in class. I'll say it again. When a double bond breaks in a resonating structure, it becomes a negative charge on the carbon. So now you have a negative charge over here. This is clear, this step.
Yes.
Okay. The rest of the bonds will just keep the rest of the bonds as it is. We are not going to change the rest of the bonds. This is one structure that we get. Oh, okay, okay. I forgot a very important thing apparently. Here, we need to have a nitro at ortho position. That was the whole point of making the resonating structures, right? So, yes, that does not change any of our plans. We still are in the same thing. So this step is a slow step. We'll write it as a slow step. Now, again, same line of reasoning. This double bond cannot exist anymore. So this goes to the next carbon, becomes a negative charge over there, right? But this still has the nitro group attached to it. Now, the nitro group, I will open up the nitro group so that it's clear how resonating structures would look like. Gaurav, are you ready?
Yes.
So NO2 group would look something like this. N double bonded to oxygen on one side, single bonded to oxygen on another side. The single bond oxygen will have a negative charge. The nitrogen will have a positive charge because the nitrogen has four bonds. Nitrogen with three bonds is a neutral nitrogen atom in a molecule. Nitrogen with four bonds is a positively charged nitrogen atom. Now, this is the structure we are at. This is a resonating structure 1. Okay, now how do we move forward from this? The negative charge that is there on this particular carbon I've starred. This carbon has a nitro group. Nitro groups are electron withdrawing, that is their entire identity. So what happens then? This negative charge can be withdrawn by the nitro group. So negative charge goes here, becomes a double bond. We'll see this in the next resonating structure. What happens if this becomes a double bond? The double bond to oxygen goes, one of the uh, pairs of electrons from the double bond goes on to the oxygen atom, becomes a negative charge on oxygen. And so when we do that, the next resonating structure will resemble something like this. OH and Cl are here as they are supposed to be. This is a double bond now because we've moved the negative charge. Nitrogen, this oxygen, which was earlier doubly bonded, now is singly bonded with a negative charge. Where did the negative charge come from, Gaurav? Are you following?
Yeah, because it has gained one electron from the covalent bond from nitrogen.
A pair of electrons.
No,
Any
uh,
single bond is one pair of two electrons.
but
Okay.
out of those two electrons, one electron belongs to oxygen itself. So it gained one electron from nitrogen.
Yes, it gained one electron, but the bond is consisting of two electrons. That's the point here.
Yes.
Make sense?
Okay.
Okay, great. Shall we move? This
Sure.
nitrogen has, okay, this nitrogen has a positive charge here because nitrogen, again, four bonds to nitrogen means a positive charge, right?
Right.
And these two bonds, which were there earlier, we did not change them, so they stay as they are, right? Okay, now what
Absolutely.
happens in the next step? When we go to the next resonating structure, how would that look like? We have to make the arrows for that. Once the nitro group has taken away that negative charge on resonating structure 1, again we can bring it back so that we can form the rest of the resonating structures as well. So this negative charge on oxygen comes back to its original position. The double bond to nitrogen goes here, becomes a bond with the benzene ring, goes back into conjugation with the benzene ring, and the double bond which is here on the adjacent carbon now can't be there because again it violates the tetravalency rule. So this goes here, becomes a negative charge. The arrows are clear at this point?
Yes.
Okay, so now I'll just hmm. How does this look? This is OH, this is Cl, and now this is a singly bonded to nitrogen because we've moved that pair of electron. This is doubly bonded to oxygen because we've moved it back. And again, we have one oxygen with negative charge. Nitrogen here has positive charge, right?
Right.
What happens next? Now we have a new bond here. Yes, Gaurav?
Yes.
And a negative charge here and another bond which was earlier there, right?
Right.
Okay. And what about the next step? The next step, this negative charge becomes a double bond. This double bond becomes a negative charge on the carbon. Yes, Gaurav, you're following?
Yes.
Okay. This structure, we'll call it resonating structure number 3. Now, what happens next when that takes place? We'll now club NO2 together as NO2 because that resonating structure part of NO2 is done with. So this is the bond that was there originally. Now this negative charge becomes a bond here, and that bond becomes a negative charge over here. This still in line with OH and Cl at the carbon. This is clear, this structure. This is
Okay.
resonating structure number 4. Any doubt?
Um,
Okay. And the last thing that we can do is this negative charge becomes a double bond that will violate the tetravalency of carbon. So this will yank out, or this will throw out the chlorine and effectively completing nucleophilic substitution reaction. OH will substitute chlorine, and this step is a fast step. And what do you see here? The final product that we will get is, now the bonds will look something like this, flipped from the original image that we started with, the original structure that we started with,
mhm.
NO2, and here instead of chlorine, you will have OH. What happens to
Okay.
that Cl? That Cl becomes Cl minus, our leaving group. They are aware of what a leaving group is. We've got this.
Yes. Absolutely.
Any problem here?
Mm. I'm good. Thank you.
Okay. Okay. Shall we continue? Next thing?
Sure.
Okay. Now I'll do the resonating structure of para position, electron withdrawing group at para position a little faster because I expect you to follow up with this now since you've looked at one of these structures. So we start with chlorobenzene, the usual thing. Now chlorine has 3 pairs of electrons on it, lone pairs of electrons, and this is a benzene ring that we have. Now our nitro group or electron withdrawing group is at para position because we are looking at para position, the resonating structures at para position, how that is affected. Yes, this plus the new nucleophile OH minus. Gaurav, we are connected, we are in line.
Yes.
Okay, so again, this new nucleophile attacks at the carbon which contains the chlorine, so that the first step that we look at is a slow step, just how we did before. I'm going to do it a little faster, guys. If you do not understand, you can slow down the video and look at it again. Look at the resonating structures, please. So this, again, OH gets bonded here, fluorine still stays on that same carbon. How does that affect us? Now the carbon can't be pentavalent, so this double bond moves on to the adjacent carbon, becomes a negative charge. The other bonds which were there earlier stay as they are, right? And this is NO2 that we have. Is it clear?
Mm-hmm.
Okay, what happens in the next step? This is resonating structure 1. What happens in the next step? This negative charge becomes a double bond. This double bond now becomes a negative charge on the carbon, adjacent carbon atom. So then
Yeah,
we can have a pair of resonating structures where what will we see? OH, Cl bonded as they should be. This negative charge which came here becomes a double bond, right, Gaurav? And
absolutely.
nitrogen NO2 will write it opened up. So N double bonded to oxygen on one side, single bonded to oxygen with a negative charge, and nitrogen has a positive charge, right? This is how we drew NO2
Right.
the previous case also. This negative charge comes onto the carbon because the double bond broke and the negative electrons are on the carbon. Now, this double bond was there before, we did not change it, so it stays as it is. This is resonating structure number 2. You've got this? Hello?
Yes.
Okay, now moving on. Now, how does this affect us? This negative charge can now be pulled by the nitro group and will become a double bond here. The double bond moves to oxygen to become O minus. So the next set of resonating structures would look something like this, with OH and Cl on one side, a double bond here and a double bond here. This was there earlier. Now this negative charge becomes a double bond on nitrogen. Oxygen double bond breaks, becomes a negative charge on oxygen, and this oxygen also has a negative charge. This nitrogen has a positive charge, right? Gaurav, we've got this?
Yes.
Okay, this is resonating structure number 3. Now we'll move back the negative charge from oxygen back onto it as a double bond, like we did in the previous case. And this double bond on nitrogen moves to the next, moves into the benzene, into conjugation with benzene, and becomes a double bond there. This will break tetravalency of the carbon, so this double bond becomes a negative charge on this carbon, right? Gaurav, you're
Right.
following?
Yes.
So that gives us the next set of the next resonating hybrid, canonical structure, resonating structure. This is how it looks like. Now, this bond was there before. This becomes a new bond, right? We look at the arrows. This becomes a new bond,
Mm-hmm.
yes. And this
Yes.
is single bonded to nitrogen, double bonded to oxygen over here. This oxygen already has a negative charge, and nitrogen has a plus charge. Yes, we are on the correct path with a
Yes.
negative charge on this carbon. Yes, this is structure number 4. And now we can conclude it by moving the negative charge here, making it a double bond, and throwing out the chlorine to complete our nucleophilic substitution reaction. This step is a fast step, and the product that you get here would look something like this. Double bonds are inverted now. This is your NO2 group. Here you have OH plus Cl minus as your leaving um, group, right? Leaving
Right.
ion, leaving group. Got this?
Absolutely. Yes.
Okay. Before I move to the resonating structures at meta position, I will give out a question. Oh, sorry, this is not the thing that I was looking at. Uh, Wait, just hold up 1 second. I'll just put the question on the screen. Okay, so this is your question. I'll increase the font size so that you guys can see it. Wait, let's make this 24. Yeah, okay. What is happening? Can you see this?
Mm,
Oh,
yes.
I moved it a bit too far. Okay, I'll just give you a second to maybe take a screenshot or whatever you're doing. Look at this question, write this question down, maybe pause the video, write this question down, and write the answer. By Monday, I should see the answer. Even if you plan to remain absent on Monday, you know I'm going to hound you for this question. So answer this question and bring it back to me. The meta position resonating structures, I'll make another video. I have a time limit of 30 minutes for one video. I'll make another video. Make sure you answer this question. I'll put up a second video for meta position. Also watch that video. Okay, give me 1 second. I'll close this recording session, Gaurav.
Okay. Thank you.